possible region or the explosion steps of classical novas Delphi in 2013 with different kind of mechanism happening on the surface or inside in the white dwarfs, kind of magnetic distortion or rotation. He used advanced telescopes such as Mount Abu infrared telescope, Himalayan Chandra telescope, European Very Large telescope, infrared telescope, and the Hubble Space Telescope also. And one of the key members working on the right now sir is discussing commissioning the 2.5 meter class telescope at the Mount Abu Observatory, which will be the second largest telescope in India. Apart from the research, sir is very dedicated science communicator. He has delivered more than 180 public lectures and organized over 60 workshops on various scientific subjects, engaging audience across the country and supporting aspiring young scientists and as well as all the students who are very curious in this wider community. Today, give us a virtual of the astronomical observatory. So be ready and mute yourself. Query we will discuss at the end. So write in the chat box or you can raise your hand also. Let's, without further delay, invite Dr. Joshi. Thank you so much, sir, for accepting our invitation and especially for quick response on the email. Giving your valuable time, we are really privileged and as well as excited to hear from you. It's over to you, sir. Thank you.
Thank you, Suman, for lots of brief introduction. I'm happy to, get this opportunity from the organizers, the Nakshatra Club from IIT Hyderabad, to interact with the young minds of the institute. I also thank Mayuk, my old office mate. We had some common wonderful, memorable time at Ayuga.
Right.
We were doing postdoc. Right? So I'm sharing my screen. Entire screen I'll select. Share. Let me know if you can see my screen.
Yes, we can see.
You can, right? Okay, yeah. So I'll try my best to make this talk as simple and as, I would say, non-technical as possible. So the prime purpose of this talk is to introduce the audience how an astronomical observatory look like. You know, most of the time when we hear about telescope, most of the time what we visualize is as a tube, cylindrical tube with few inches, few tens of centimeters in diameter, made up of small mirrors where there is an eyepiece. We can put our eye to see through the telescope and we see some beautiful planets or other celestial objects and all. But when we talk about the telescope involved in professional astronomical, astrophysical observations, they are little or I would say quite a lot different from what kind of telescopes we operate at our amateur hobby level. So I'm going to introduce my alma mater from where I did my PhD, my first postdoc, and now I'm pursuing my research through this facility. So I would say it's my second home. That is the Mount Abu Observatory. I'm going to introduce this observatory, and we will also, through this talk, we'll also have some flavor of some type of some interesting astronomical objects also. So starting with my talk, here you see the web page of my institute, Physical Research Laboratory. Physical Research Laboratory was established by Dr. Vikram Sarabhai immediately after the independence, so in November 1947. So PRL has just celebrated 75 years, the Amrut Mahotsav. And from 57 till 60s, Vikram Bhai has established various groups focusing on different aspects of physics, physical research. At the same time, he has also visualized and conceptualized the development of space technology in India. And PRL became the cradle of space technology in India. So the ISRO, Indian Space Research Organization, actually born in PRL, and eventually in late 60s, when it started growing and need more space and resources. So ISRO became independent institute from PRL. So PRL is considered to be the cradle of space science in India. In PRL now we are focusing on various aspects of physical research like atomic, molecular and optical physics, geosciences, planetary sciences, space atmospheric physics, theoretical physics, and also we have a dedicated observatory studying the sun. We have one division focusing on studies of astronomical objects, celestial objects. So there is astronomy and astrophysics, where I am working. So in our division, astronomy and astrophysics division, we are working on various type of celestial objects and phenomena happening, like solar system objects, comets, asteroids, dwarf planets, etc. We study the formation processes involved in the star formation. We discover and characterize exoplanets a little more on this topic at the end of this presentation. We study the dying phases, the death phases of the star and binary star also, which are known as novae and supernovae. So we also study the interaction of two nearby, very close by stars and the phenomena occurring which produces huge amount of high energetic radiations called X-ray binaries. And all these objects are primarily lying in our own galaxy. But apart from all these galactic objects, we also study extragalactic astronomy also. So our scientist in our division uses all kind of observational facilities, starting from ground-based facilities to space-based facilities. But our prime facility, that is the Mount Abu Observatory, I am going to introduce. But before that, there is a common misconception in a layman mind that astronomy research is very easy. If you have a good quality telescope, you just point the telescope to a star, see through the eyepiece, and you will see a beautiful movie, colorful movie. You see in that moving things, you see through the telescope, you write down all these details, and that is called an astronomical research. And that's why people feel that, okay, if we have a good telescope, we can see through the telescope and we see all the phenomena happening in the universe. But it's not true. Let me explain. See, the image you see here, it's a kind of a pepper and salt kind of a noisy image, where you see three bright dots. One dot, the lower right circle, is marked with two horizontal lines. So these three stars I have acquired in my image. So we use CCDs attached with the telescope and get an image. So here we see three stars. Again, if you see one star size, one star spot is a little bigger compared to others, does not mean that this star is actually bigger. It means that this star is brighter. It can be smaller star but quite a nearby star. So it appears bright star. So there is no direct measurement possible with this image. So suppose I study this particular star, it appears very boring, white colored dot in the image. But if I keep monitoring the brightness of the star, if I keep monitoring how the brightness of the star changes with time, I will see that in different wavelengths, in different colors, the star brightness changes dramatically. It shows some kind of aperiodic flickering on top of some periodic modulations. That is interesting. We further study the same star using spectroscopic techniques. So I produce the spectrum of the starlight coming from that star, and I see that, okay, this star light is showing an emission spectrum, primarily, dominated by hydrogen, helium, and some other heavy elements. I also, study some of the emission features and produce the radial velocity. Oh, most of you, I believe, know the radial velocity. That is called Doppler effect. So, using the change in the wavelength of this kind of features, we can so we can measure the velocity of the star directly. And I use the mathematical model, the known physics known from the terrestrial experiments. I use those mathematical model to understand the observations I have made. And using all this painful, long, time-taking process of studying just one star, I get the impression, the idea of how this star actually looked like. And then I come to know that the apparently boring star in this CCD image is actually a very beautiful binary star system. It is not a single star, though it appears single star here. It is not single star, it is actually two stars, when one star is much cooler than our sun, also smaller in size, and the other star is heavier than the sun, but much smaller in the size compared to the sun. So that is the dead remnant of a star called white dwarf. And then they are very close to each other, and the plasma, the material from one star get accreted around the other star and forms a disk, and so on and so forth. So all these details I cannot directly see in this image, but all these observations, analysis and modeling help me gaining this information. So astronomy, research in astronomy is more like, a job, detective job. We have to be a detective. We have very limited information. In physics, chemistry or biology, we have a lot of freedom. We can develop our own instrument, our experiment. We can use different type of substances and material in the experiment. We can change their conditions, their temperature, pressure, densities, composition. All these things we can, we can set in the experiment, and eventually we run the experiment and see what happens. And then we know. In physics, chemistry, biology, this is possible. In case of astronomy, we are literally handbound. We cannot, go to a star, put a thermometer in the star's mouth and measure the temperature of the star. Can we? No. We cannot go to a nebula and request, please change your pressure and density. We would like to see what happens. We can't do anything. In astronomy, we simply study naturally established laboratory, the whole universe. The universe we consider a naturally established laboratory. We can't change in the laboratory setup. What we can do is we observe those setups, various celestial bodies, and then try to understand what is happening over there. Well, few tens to few billions of light years away from here, sitting on the earth, a very tiny dot compared to universe, sitting on the earth, knowing about all the universe is really fascinating job to us. So with this idea how research in astronomy works, I will move to the main topic of my talk. So as I said, this is our observatory, the Mount Abu Observatory. You can read here, it is the Mount Abu Infrared Observatory. Infrared because this is the first ever observatory dedicated to infrared observations in India. This is India's first ever infrared observatory, and this is one of the 5 largest observatory in India. So the observatory situates at the western part of India in the Aravalli range. I hope you can see this video, right?
Yes.
So it situates at the highest point in the Aravalli mountain range called Guru Shikhar at Mount Abu Observatory, and you can see the scenic view of this observatory. You can see there are 3 structures. This is one dome. This is the second dome, much larger. There is the third dome, and there are two more domes. You can see there is a small dome here as well as here also. So in total, this observatory houses 4 telescopes. One is the old 1.2 meter telescope. This is the Bhisma Pitama of this observatory. This telescope started working since early 90s. So it has completed almost more than 30 years indeed. Then we have 2 small telescopes. One is the 50 centimeter telescope. The other is 43 centimeter telescope. And finally, the latest addition in the observatory, that is the 2.5 meter telescope, which is India's second largest telescope now. The largest one is 3.6 meter telescope in Himalayas, close to Nainital. There is a telescope called Devasthal Optical Telescope. So that is the largest one. This is the second largest telescope. What this number belong to, this 50 centimeter, 43 centimeter, 1.2 meter or 2.5 meter, what are these? So I'll explain in detail, but basically these are the size of the primary mirror of the telescope. I will come to this point why it is important. Starting from the 1.2 meter telescope, the detailed introduction to this old but still efficiently working telescope. So this is the building you can see. The building is 3-story building, and on top of this 3-story building there is a dome-like structure, and in the middle of the dome you can see some slit, some vertical structure also. So this dome is not actually steady, it is actually a moving component. You can see a dome is rotating. And the telescope is preserved within this dome. This vertical slit shutter can also open. You can see the shutter is opening here, and from the opening you can see this blue color telescope. The telescope movement also you can see, though it is moving quite irregularly, but it is otherwise its motion is very smooth. This is actually the fast forward mode of the video. So the telescope is always situated, it's preserved well within this dome. The dome protects the telescope from heavy wind, heavy fog and other climatic changes. In the daytime the shutter is closed, the telescope is protected, but in the night time we open the shutter, and through the shutter telescope can see the sky. Now this telescope should see any point of the sky, and for that this shutter also need to be synced in any part of the sky, and hence the dome motion is required. Here you can see the structure of the telescope. The telescope itself, the telescope itself is a hollow body. Usually you have seen the telescope structure as a complete covered body, but this is India's first ever infrared optimized telescope, and all infrared optimized telescopes do not have covered body but has just a skeleton like frame like structure. In the bottom of the telescope you see a cylindrical part in which the main mirror of the telescope is housed. The size of the telescope you can compare with an average human body. The diameter of this mirror is 1.2 meter, and it is almost comparable to an average human body. That okay. So that telescope is mirror is protected in this cage. This is called mirror cage. And why the size of the mirror important? So again, one of the misconceptions about the telescope is we believe that the primary work function of the telescope is to see things bigger, magnified. But that is incorrect. Even the best available telescope on the earth today, the best available telescope cannot resolve a far lying star in the details so that we can see the features of the star. No. Even for the biggest telescope available, a star is just a point-like, a dot-like structure. You cannot resolve any star to great detail. The telescope is not made for zooming the picture. The primary function of the telescope is something like to see the faintest star. See, our eye has a limitation looking at the faint stars because the amount of light, the flux from these faint stars is so feeble that it cannot, get collected from our cornea and detected by retina because the size of the cornea is very small. But if you want to collect more light to see that faint stars, you need larger collecting area. So this mirror provides much larger collecting area. All the light falling on this mirror is actually concave mirror. So all the light falling on this concave mirror get reflected and focused on the top part of the telescope. And there you can see, okay, or you will see here, yeah, there is a small mirror here available. So that mirror is actually a convex mirror. So the focused beam from the primary get reflected back to the primary again, but again in the focused mirror. There is a small hole in the center of the primary. So finally focused beam passes through the center and focus just below the telescope. So telescope has done its job. The telescope has collected the large amount of light from larger area and focused it into smaller part. From here, the camera comes into the play. I will come to that. But before that, this telescope should point any part of the sky and look at any star. So for that, the telescope required two rotational motions. So two rotational motions about two orthogonal axes. So this is the first motion. The tube is rotating around this U-shaped fork. So the whole tube rotates around the U-shaped fork in one axis, and the U-shaped fork itself rotates in the orthogonal second axis. And using these two rotational motion, the telescope can point to any part of the sky. Here you can see the telescope is moving, the whole fork is moving around its axis, and telescope is pointing to a star. When telescope is pointing to some specific part of the sky, the dome also should follow and bring the opening, the shutter, in line with the telescope. So for that, the dome is also moved synchronously with the telescope. Here you can see the motion of both the telescope and the dome simultaneously. Moving this large structure so smoothly from the dome itself is really, exciting experience. So as I told, when the telescope gives the focused light just below the telescope, the role of camera comes into the picture. We can place different type of cameras. It can be an imaging camera, it can be a spectrograph to produce the spectrum from that focused collected starlight. It can be a polarization measurement device also, which we call polarimetry. So a polarimeter. So, with one single telescope, we can place different instruments depending on our requirement. A scientist decides what kind of measurements he wants or she wants, and then the camera he or she opts. So here you can see, yes. So two of our engineers are actually mounting a camera with the telescope. So these camera are also very sophisticated camera, highly sensitive, very little, almost negligible noise, and high quality optics and detectors. So we use CCD or CMOS detectors for optical measurements, or other kind of infrared arrays for infrared measurements. Earlier, the telescope need to be operated from the dome itself, and it was very painful because the conditions are very harsh. But now, with this advancement of technology, we have a dedicated control room from where our engineers, can operate the telescope from a control lab using these consoles, or even directly using the computer. So we click on a specific star of the sky chart in the computer, and the telescope will move to that star. So things are highly automated now. And here you see the beautiful sky just above the observatory. The observatory sky is much clear, primarily because the observatory is situated at high elevation. The elevation of Mount Abu Observatory is just little less than 2 kilometers. Some of the observatories, like our Himalayan Astronomical Observatory, is almost 4.5 kilometer elevation, and for many years it holds the record of the highest elevation observatory. Now the other observatories are even at high elevation. Okay. And here you see the motion of the stars in the sky. So this is not the picture of the single star. It's not a snapshot of a sky. It is actually the trail made by the moving stars, the rising or the setting stars. So if I keep the shutter of my DSLR open for an hour or two, I will not only take the picture of the star, but also take the trail of the motion of the stars. So these are called star trails. Those of you who are in astrophotography knows these star trail pictures very well. So you can see all these stars are moving in large circle, but as you are moving towards the center, the motion of the stars are smaller, and eventually if you see, there is a relatively bright star moving in a very small circle. This star is again not a very bright star, it is pole star. The star very close to our rotational axis of the Earth. So this pole star is a 5th magnitude star, not a bright star, but it is special because it is lying very close to the center of the star. Quick introduction to the other facilities, like this 50 centimeter telescope situated in this small building. So you can see that is again mounted on a small U fork shape part, and one of our PhD student is aligning the telescope in the daytime and make it ready for the nighttime observations. The other 43 centimeter telescope is housed in a different kind of a dome. The dome in the nighttime, the dome opens completely, and the telescope can point to any part of the sky. Now you may ask, if we have such bigger telescopes, 1.2 meter or 2.5 meter class telescopes, why we need this smaller 50 centimeter, half a meter class telescope? But the point is, observation time on the larger telescopes are highly competitive. Many scientists need observations from this large telescope. So if I have some project where I want to monitor a single star or a small part of the sky for a very long time, I cannot get that long time observational time on big telescopes. But there these small telescopes come into rescue. Using these telescopes, we can run monitoring kind of a project where we can monitor a specific star or group of stars for a long time and produce some interesting scientific results. And this 2.5 meter telescope, now I would say it is not upcoming. Earlier, the telescope has seen the first light in 2022 October only, but still it is in testing phase, and it will be open for observation, the regular observation from next winter. Though we have obtained some observation and also published some of the primary results also from this telescope. So if you compare the mirror size of the telescope, it is much larger compared to both the 1.2 meter telescope as well as with the average human body. You can see the diameter of the telescope is double than the 1.2 meter. But what matters is not simple diameter, it is actually light collecting area. And we know that the area is proportional to the square of the diameter. So that way, in terms of light collection, this 2.5 meter telescope is at least 4 times better, not twice, but 4 times better than the older one, 1.2 meter telescope. And here is the picture of the 2.5 meter new facility. You can see it is mounted in different type of those. Here also it is mounted in a U-shaped fork, but this fork is mounted horizontally on this circular plate. So the motion is vertical, horizontal combined motion. The vertical elevational motion is made by this telescope tube in this horizontal axis, whereas in order to move the telescope azimuthally, the whole circular platform will rotate. So this whole circular platform will rotate, and also telescope tube will rotate orthogonally, and it will point to any part of the sky. Coming to the other interesting aspect of our research, what all objects we observe using these telescopes. So I'll introduce some of the interesting objects. You all may have heard about all these telescopes. So one of our group is focusing on the studies of comets only, and they picture the comet, but not only picture the comet, they also get their brightness, polarization, and spectral information of these objects also. The image you see here is not acquired using our telescope. It is acquired using a DSLR camera. So you will see a wide field image. The angular size of the image is few degrees to it may be few tens of degrees. Here you see a comet. There are sharp point-like stars in the background, whereas there is a fuzzy structure here. So this is a comet, and comet has two tails. One is a blue color straight tail, whereas one is a white, yellowish white color curved tail. And these tails are called, this is called dust tail, mainly made up of dust and gas. And this is the ion tail, so primarily made up of ionized gas. We'll not go in detail of the reason of these two tails and all, but this is really an interesting object. Every year we discover, few tens of comets, but none of them are bright enough to see through naked eye. You need at least a good quality binocular to detect these comets, or amateur level telescope. But once in few decades, you will find a comet which is very bright. You can see through naked eye. Like in 1980s, mid-80s, famous Halley's comet have visited the Earth. It will again visit in 2065 or so. This is another very bright comet. Visited the Earth sky in 1996. If we see the comet through our telescope, we can cover very small part of the sky, because the telescope field of view is most of the time not very wide. It is very small. So we can see just small part of this comet. But if we use our spectrograph to collect the light and produce the spectrum of this small part, or even the smaller part of this small part, then we see this kind of spectrum. And here you can see the spectrum is rich with the various emission bands and lines. And I have also marked some of the molecules producing this band. So this we can say that this cometary material, the dust, is reaching CN, C2, CO plus, even CO, C3, and all these kind of molecules are available. Some of them are, ionized molecules also there because of they are exposed to very harsh ultraviolet radiation of the sun. The other interesting object is various type of stellar objects. So here you see an image of a small part of the sky where you see many stars scattered here and there. But in the center of the image, you can see that there is a region, a small region where number of stars are, situated together, and that is, like a cluster. And this is actually called star cluster. If you zoom this region and take the picture with a telescope like ours, you see there are, thousands to tens of thousands to sometimes, hundreds of thousands of stars lying in this small region. So this is the picture of a cluster known as a Messier 2. That is a globular cluster which is around 55,000 light years away from us. And the diameter of the cluster itself from this end to this end, the diameter itself is very large area. It is 175 light years. So light takes 175 years to reach from this end to this end. The cluster is very old cluster. The average age of the cluster is roughly 13 billion years, maybe a little less than 13 billion years. So this is one of the oldest object in our galaxy. And number of stars also you see, it is almost 150,000 stars. So this number is again not a perfect number, but this is a good level estimation of number of stars in this galaxy. So this type of very exotic objects are also there. The other type of objects we do study are the giant explosions in the universe. They are called supernova explosions. So you can see a galaxy here, and there is a arrow marked here. You will not find any object marked by that arrow. But if you see the next image, you will see that there is a star just next to this arrow. And in the third image, the star has brightened up. So there was no detectable star here. There was no star detectable here. But suddenly a star appeared, and the star became brighter and brighter, right? So this kind of explosions are known as a supernova explosion. This any star can went into supernova explosion in any galaxy, not in our galaxy, but in other galaxy also. The star has to be massive, much should have larger mass compared to our sun. Our sun will never go through this supernova explosion phase. When a star becomes a supernova and reaches its maximum luminosity, you won't believe the light coming from this star outshines the whole galaxy. The galaxy made up of 100 billion stars. So a single star during the maximum of the supernova outshines the 100 billion stars together. So it's a really, really explosive event, when this kind of a supernova happens, the star will lose 99% of its mass into the space. And this mass will thrown away into the space with very high velocity of the range of 10,000 to 30,000 kilometers per second. So in 1 second, this gas will expand to 10,000 to 30,000 kilometer velocity. And they will produce a beautiful, expanding nebulae. So all these pictures you see here are the real nebulae. The color may be real color, maybe pseudo color, but you can see the varieties in the color and in the shape of this nebulae. So all these nebulae have found by one or the other supernova. And in many of these nebulae, you can see the central star also. Like you can see a central star here, which is now a neutron star, but earlier it was a supernova which thrown away this nebula. So in most of the images, you will see the central star also. We do study various galaxies also. And usually we familiar with this kind of spiral structure of the galaxy. Our own galaxy, the Milky Way galaxy, is also spiral in shape. But not necessarily all galaxies are spiral. Some of the galaxies have no specific shape. They are very elliptical, dull shaped galaxy. Some are spiral galaxies with all the spirals meet in the center. Some of the galaxies are spiral galaxies, but in the center they have a horizontal, they have a elongated bar. So they are called bar galaxies. Even very few, rarely, the galaxies are in shape of ring. Instead of the complete planar structure, it forms a ring-like structure. So this is a ring galaxy. And not only that, now it is almost established firmly that all these galaxies host a supermassive black hole in their center. The supermassive black hole are gigantic black hole which has a mass almost 100,000 to millions of mass of the sun. And it's a very massive black hole. And such black holes are there in most of these galactic centers. And sometimes these black holes eat the material situated around it, and they become active. They produce huge amount of energy as well as also throws away material. The black hole itself will not throw away material, but when the material will accrete onto the black hole, just before reaching the black hole, the material may be thrown away in jet-like structures. So here you can see an active galactic with two radio jets. So these jet-like structures are very bright in radio wavelengths. So even galaxies are also in vast varieties in that galaxy. These galaxies do interact with each other too. And here you can see if two galaxies come close to each other and interact with each other. Now remember, these galaxies are not a solid structure. They are made up of nicely arranged but very sparsely arranged stars. So galaxies are in a way hollow structure in which the stars, 100 to 200 billion stars, are sparsely arranged. When this galaxy come close to each other, even they pass through each other, they will not collide directly because they are not solid object, but they will penetrate through each other, and during this penetration, the structure of both these galaxies will get disturbed because of each other's gravitation. Here you can see these two galaxies are coming close to each other. Here they are passing through each other and changing their shape. In this image, they have passed through each other and got disturbed largely. Here also, right? So this way, the galaxies interact with each other also, and we have captured these images and these processes. Using computers, now the supercomputers, we can simulate this kind of processes also. In our observatory, as I have already told, we do discover and characterize exoplanets also. So exoplanets are planets revolving around the other stars. So till 1995, before 2 decades ago, we knew about only 8 or 9 planets in the solar system. But now we have discovered not hundreds, but even thousands of planets revolving around the other stars. They are called exoplanets. In year 2018, we have discovered an exoplanet, and that was the first ever exoplanet discovery from India. And media, highlighted this discovery, the first ever exoplanet discovery from India, from our division, from our group. And later, our Prime Minister, Shri Narendra Modi, also congratulated our team for this discovery of first ever exoplanet discovery of India, tweeting on his official Twitter. So with this, I have given you a flavor of how an observatory look like, how it functions, and what it functions for. I hope you got a reasonable understanding of how this observatory works. Thank you. Thank you very much.
Thank you, Professor Vishal. It was really nice to see. I mean, so much diverse works are going on in the evening, and you have so many, I mean, different types of telescopes. I hope like the students who are attending, and if you don't mind, is it okay if we have this recording of your videos in our YouTube channel? We have a channel. Yeah.
Yeah. You can keep it. You
Yeah,
can keep
actually,
it. No.
some faculties also requested because they could not join. They want to see it, so that's why they. Okay.
Sure.
Okay. Uh, okay. So, anyone have any questions for Professor Vishal?
Yeah.
You can unmute and say your questions. Fine. So, Professor Vishal, I have one question before others. So, this supernova observation strategy, like how do you manage, like for example, when you get to know like there is a supernova, or how do you make a plan for that?
So that's an interesting question. Now, how do we know where supernova come into explosion? So people, I mean, there are amateur astronomers keep watching on various nearby galaxies. They keep acquiring images of these nearby galaxies very frequently, very regularly. I mean, sometimes almost on daily basis. And then they keep these images. They compare these images with each other, either manually or programmatically. And they look for some newly discovered star. So amateur astronomers contribute a lot in discovering this supernovae. Nowadays, even we have various optical survey telescopes are also there, which in robotic fashion scanning the sky every few nights and then look for this kind of new supernovae. And with the availability of bigger and bigger telescope for this survey purpose, we start discovering tens to even hundreds of supernovae every year.
Oh.
But almost all these supernovae are too faint to study through even small telescope also. So rarely one or two supernova. Somebody is yeah. So rarely a supernova or two are bright enough to be studied by a small telescope or maybe seen by the binocular. In 2014, we discovered a supernova in a galaxy which was very bright and very nearby. So yes, this way we started discovering hundreds of supernovae every year. Most of them are very good.
Okay.
Yeah.
Nice.
Hello, sir. Can you hear me?
Yeah, I can hear you.
Okay. Apart from that, if you are getting the supernovas, then we can do the data analysis and then study their properties also. So, in
Yes.
which way you are doing on that way?
Sorry.
If we are getting the, you told na armature astronomers are helping us to,
Yes.
to
Yes,
find
yes.
supernova different kind of galaxy.
Yes.
So we can get out their properties also, like which kind of supernova they are, what is their magnetic properties, or how they are formed.
Yes. So yeah, I understood your question, Suman. So discovering a supernova is one thing where you just need to compare an image, the recent image, with a template image, and you need to look for a newly detected star. But if you want to study that supernova in detail, like you want to classify which type of supernova it is, or what kind of phenomena is happening, at what velocities it is throwing the gas and all, then you need either little sophisticated facilities like spectroscopy is a key technique to understand the supernovae. And spectroscopy of a faint supernova needs large telescope. The other possibility is one can follow the supernova and see how the brightness of that supernova changes with time. And they are called the light curve of the supernova. If one obtains the light curve of the supernova, then using known physics, the available models, one can get some basic information about that supernova. So discovering is easier for amateur astronomers, but studying the supernova in detail needs actually large telescope. So, it's kind of a symbiotic system. Amateur astronomers discover supernova and alert us, and then we start observing those supernova with bigger facilities and get the information about the supernova.
Okay. And one last question from my side. So, if some students want to have some observations from your 1.2 or 2.5, let's say, what is the procedure for proposal submission or writing or?
Okay, so if some of the students or even postdoc or faculty have some ideas and want to acquire some observations, they can contact any of us, any faculty of astronomy, astrophysics division, and we, in collaboration, we coordinate those observations with our telescope. We also help in basic data reduction and all, and maybe in analysis also. So this way, the student can directly approach us with the idea he or she has.
Okay, that would be actually really nice.
Thank you.
One more question. It's public for to visit because I am from the Rajasthan and I want to go to that.
Oh, yes. So it is
for everybody, or we have.
Yeah. So the telescope observatory itself is not open for public to visit, but at the same time, I would say we run an outreach program where we invite students, amateur astronomers from various institutes or so, and allow them to visit our observatory primarily in the daytime. Because in the night time when observations are going on, we do not allow them. That's not possible. But in daytime, students can visit and have a look at the facility itself. So you, Suman, you are also welcome. You simply write to me and I will arrange your visit. Any other student, or I would say a student as a group, I mean the Nakshatra Club itself, can plan an academic visit to our observatory. You can have a wonderful visit to the observatory and also have good time at the hill station. Mount Abu is a hill station.
Okay, so, that would be really, really nice. Yeah, definitely we'll think about making a plan and then go together as a group. That would be nice. Okay.
So,
thank you very much, Professor Vishal, for your really nice talk, and hope I think people will have enjoyed it, and then once we'll upload, then many people, they can contact you also, they can write email regarding all other things. Thank you very much.
Thank you. Chalo, nice.
Okay, bye.